Okay, welcome everyone to this week's BTPC IDEA Series seminar. Today I'm happy to introduce Mojtaba Najafizadeh. He is a research associate at IPM, which is in Tehran, Iran, and he'll be talking today about some of his research on spin gauge theories. So we're all very happy to have him here today, and please take it away.
Okay. Hello, everyone. Thank you very much for giving me time to give a talk here in BTPC Launch Idea Series. You can see my cursor?
Yeah, we can see.
Okay. My talk basically is depend on this paper, which was submitted last year, but I'm using the results of these two papers with collaboration with Jihad Murad, Xavier Bekar, Jihad Murad, and Mohammad Reza Setare. Let us start with terminology. Historically, the term lower spin was referred to renormalizable quantum field theories in the past, but today, lower spin refers to consistent classical field theories with spins less or equal to 2. However, higher spin stands for problematic construction for spins greater than 2, which these bosonic higher spins are known by Franzdal action in 1978, and for fermions, fermionic higher spins with Franzdal action in 1979. When you are studying a particle of a spin 4, you are dealing with higher spin theory. In addition, higher spin also refers to theories containing an infinite tower of all spins. For example, in Vasiliev theory or in Segal theory, Segal formulation for higher spin, we usually use an infinite tower of all spin. So if you consider all spins from 0 to infinity like this tower, your field is a bosonic higher spin. And also for fermions, you have such a tower. But continuous spin particle, in short CSP, is an infinite chain of all spin states characterized by continuous spin parameter called mu, which mu controls the degree of mixing of different states. For bosonic CSPs, we have such a field, for example, naively, and for fermionic CSP, we have this shape. This mu controls the degree of mixing of these states. This is why I called this infinite chain, but for the previous case, for higher spin, I called it an infinite tower. When mu goes to 0, yes.
Can you have
Please.
mixing between 0 and 2 and have spin continuous?
What? Mu
Can you have the
to
spin, the mixing between 0 and 2? So from 0 and 2, you also can control the spin, or you need to have the overlap between 0 and 1 and 1 and 2. You cannot have the 0 and 2.
You should have all the spins, and the degree of mixing of each state should be equal. This is mu, and but this is a naive shape, you know. I wanted just to show that what is a CSP in contrast higher spin field.
So do you have like the physical meaning of this mu?
Yes, we will see.
Okay,
this is just terminology. I will back to this. I mean, to this particle later in detail. Okay, you're welcome. Here, when mu goes to 0, CSP decomposes into an infinite tower of all spins. You see, when mu goes to 0, this decomposes into a bosonic higher spin. Wigner called this particle continuous spin particle, in short CSP, in 1939, but later in 1963, he called the particle infinite spin particle. This is why in literature you will see both names, continuous spin or infinite spin particle. Also Wigner particle, some people use Wigner particle in their papers. But let me call CSP in this talk. Okay. We first discuss about unitary irreducible representations of Poincaré group, which CSP is one representation of this group. Then we present Wigner equations describing this particle. Then we talk about continuous spin representation which can be obtained from massive representation. Then we discuss about a consistent gauge field theory for this particle. Mostly we focus on Schuster-Toro formulation. And then we speak about CSP interactions with matter and its supersymmetry. Okay.
Mojtaba,
yes.
Before you continue, I just wanted to quickly ask, since I'm not super familiar with supersymmetry, this continuous spin particle, is it trying to answer a specific question or solve a specific problem in the field theory, or is it kind of just a categorization of something that we think exists in experiment, but maybe isn't fully, all the parameters aren't fully understood?
Yes, maybe in the future, in the high energies, this mu can be turned on, and we can observe this particle, maybe. But you know, before 2014, there were no consistent field theory, classical field theory for this particle. This is what I want to talk about it today.
Awesome, thank you.
You're welcome. Okay, Poincaré algebra ISO 3,1 is given by these commutation relations, which P and J are 10 Poincaré generators of this algebra in 4 space-time dimension. This is 4 generator and this is 6 generator, translation generators and Lorentz generators, which is containing of boosts and rotations. These Lorentz generators is a sum of a spin operator and these Lorentz generators. Indeed, we usually set S0i equals to 0 and L0i is boost. And then we define total angular momentum as a sum of spin angular momentum and orbital angular momentum, which have these commutation relations. But here in this slide, I want to emphasize that a spin is discrete in this space, in these generators. Later, for continuous spin, I will make continuous this space. A method for classifying unitary irreducible representations of Poincaré group is to make use of the eigenvalues of the Casimir operators. For Poincaré algebra, Casimir operators are P square and W square. This is quadratic Casimir and this is quartic Casimir, where W mu is defined in this form. W is a combination of P and J, these 10 generators of Poincaré algebra, such that W square, if you compute this W square, you will get this amount. It is easy to check that P square and W square can be commute with generators of Poincaré algebra, which is why they are Casimir operators. We should find eigenvalues of these operators to classify unitary irreducible representations of Poincare group. Let us start with massive representations. For massive representations, eigenvalues of P square are M square, while the eigenvalues of W square are not so obvious. To understand the meaning of this operator, let us go to the rest frame of massive particle, which is this. In this frame, you will see just a spin angular momentum. Indeed, orbital angular momentum is 0. In this frame, P square is M square, and then W square, using this definition that we obtained before, leads to this amount. As I said, because we are in the rest frame of the particle, we cannot see orbital angular momentum. We will see just a spin. And eigenvalues of this operator are S by S plus 1. So Casimir eigenvalues for massive representations are in this form, M square and this. So massive particles, massive representations are labeled by mass and spin. Now let us go to massless representations. For massless representations, we can go to the light-like frame, which is this, and K is non-zero. It is one can find that P square is 0 by in this frame, and then W square, which had this definition, W square becomes this, which operators A and B are defined in this form. I wrote this intently in this form to compare them with the Weinberg's quantum field theory books. Indeed, this is boost in direction X. This is rotation in Y direction. And also this is the boost and rotation. And Weinberg says that eigenvalues of these two operators, A and B, should be 0. If we call eigenvalues of A and B operators as A small and B small, these this omega square, which is eigenvalues of W square, becomes minus mu square. I call this mu square, which A and B or mu are continuous parameters. So for eigenvalues of W square, there are two possibilities. Omega square can be 0 or non-zero. This says that massless representations are classified into two different types of representations, as Wigner classified them in 1939. We will discuss each one in the following. Let me start with helicity representations. As we said, for helicity representations, which is also known as finite spin representations, P square and omega square are 0. These representations describe all helicity particles, bosonic or fermionic, lower or higher spins. For example, photon, graviton, gravitino, and all massless particles, which we know, are located in this representation. Indeed, since P square is 0, you should have also W square equals 0. One choice is to consider W mu in this form, which H represents a proportionality factor. Then you can find this factor, which is nothing but the helicity operator. So helicity representations are labeled by helicity. If there is any question, don't hesitate to ask, please. Okay. For continuous spin representation or infinite spin, we had W omega square unequal to 0. This describes continuous spin particle, so-called continuous spin particle. bosonic, which has two types, bosonic or fermionic. This particle is a non-observed elementary particle. This is since this representation is a unitary irreducible representation of Poincaré group, this is an elementary particle. Therefore, helicity representations and continuous spin representations are labeled by helicity and continuous spin parameter mu. In 1947, Wigner presented two sets of wave equations describing both bosonic and fermionic CSPs, which are known as Wigner equations. In the following, we will discuss about Wigner equations, which can describe this representation, this particle. Wigner equations. Let us introduce an auxiliary Minkowski space to define the spin space. As I said, for the massless and massive representations, this was discrete. But in this case, because we should have a non-zero amount for W square eigenvalues, we consider this space as an auxiliary Minkowski space. We use eta and omega. Eta has a role like X, and omega has a role like P. So omega is like momentum in this auxiliary space, where P momentum in this space and omega in auxiliary space defined in this form, and they have these commutation relations. So we introduce an auxiliary spin space to introduce continuous spin particle. Using this generator, as W square had this form, if you use this generator in this here, since P square is 0, using just this term, you will get this operator, this amount for W square. Now, if one demands a non-zero amount for the action of W square on the CSP field, as I said, eigenvalues of omega W square should be minus mu square. And if you use this operator here, you find that this will be valid by choosing these wave equations. These are known as Wigner equations for bosons, which he found them in 1947. You see here that this non-zero amount comes just from these operators. If you set P dot d eta plus I mu on phi equals 0, then you apply eta square plus 1 on phi equals 0. These two equations are independent, but these two equations are dependent of these two. Indeed, if you compute the commutator of equation 1 and equation 2, you will get the equation 3. And using the commutator of equation 1 and equation 3, you simply can give a P square on phi equals 0. Maybe you ask that there were another choice. For example, here we could choose P dot eta plus I mu equals 0 or d eta plus 1. Again, you will get minus mu square, but you cannot obtain this important relation, which says that this particle is massless. So continuous spin particle, as we said, was a massless particle. You should have this equation, this relation. In these relations, mu, as I said, is continuous spin parameter with the dimension of a mass. And the field, phi, is given by this relation, as I already showed it by this image. These can be equal. You have a infinite chain on all spins such that these states are mixed to each other through this mu. And yes, and
sorry, I think there's a question.
Yes, yes,
Luke, you want to go ahead?
I just want to ask about equation 2.
Yes.
Is that a necessary equation, or did Wigner just add it as an ad hoc assumption to further fix the eta parameter?
No, it's a necessary equation. Indeed, you see, if you put p dot d eta here, this amount is I mu, then you should you get minus mu square, and then you should choose eta square equals -1 here to cancel this minus, because you should obtain minus mu square. This minus comes from the convention, because we are in the mostly we are working in this paper in our work. We are working in the mostly minus signature for the metric. This is why here we have a minus. If you work in the mostly plus signature for the metric, here is plus. But W had a dimension of a mass, so W square should have a dimension of mass square. And yes, so equations 1 and 2 are necessary and are independent equations, but these equations can be obtained from these 1 and 2 equations. So for example, as I said, if you choose another possibility, you cannot obtain p square on phi equals 0.
Okay, thanks.
You're welcome. And as you see here, our field is dependent on p and eta. Before, for helicity particles or massive particles, we had just phi of p or phi of x, depending on you are working in momentum space or position space. But here, because you add an auxiliary Minkowski space, you have two parameter here. You may work in position space or momentum space, and here also you may work in eta space or omega space. We will work in both space, in both auxiliary space later. For Fermi-Newton CSP field, we should add gamma matrices to the Lorentz generators. However, W square does not change. And again, you can get these equations, which are same as the bosonic case, except equation 4, which should be gamma dot p on phi or on psi equals 0. These are same as the bosonic case. And here, the field psi, the field psi has this form, which can be thought like this image. And yes, these are also mixed to each other. Okay, so in summary, eigenvalues of Casimir operators of the Poincare algebra, which can classify unitary irreducible representations of the Poincare group, are in this form. For massive particles, we have these eigenvalues for helicity representation, and these for continuous spin representations. Let us plot this function such that minus omega square is in the is a y-axis, and m square is x-axis, and the slope is s by s plus 1. If you plot this function, you will get such a image, which all massive lower spins are located here, as you see, up to spin 2, are located here. All massive higher spins are in this origin, in this in this region, and CSPs are on the are on this axis, both bosonic and fermionic CSPs, and all lower and higher spin are massless lower and higher spins are located in the origin, and solid blue lines are bosons and red lines are for fermions. Okay. Let us talk about continuous spin representation from massive representation. In 2005, Khan and Ramon illustrated that that in flat space, the continuous spin representation can be obtained from massive representation by taking the following limit, such that if m goes to 0, s to infinity, spin goes to infinity, while their product remain constant, then you can find continuous spin representation. You can see this in these eigenvalues. If you take this limit from these massive representations, you will get p square equals 0. And here, when s goes to infinity, here you have just s square, such that m square s square becomes mu square. So this is a trick to obtain continuous spin representation from massive representations. You know, until this time, until 2005, there were no equation of motion for continuous spin particle. And the Wigner equations were just wave equations for this particle. But we had no equations of motion or action principle. Using this method, taking this limit, in 2005, Xavier Beccard and Jihad Murad found a non-Lagrangian equation of motion describing a bosonic or fermionic CSP from the massive higher spin equation of motion. Indeed, they consider massive higher spin equation of motion. Then they applied this limit, and they could obtain this equation of motion for continuous spin particle for CSP. But this equation has a constraint on the gauge field, on this field, which is this. This is a constraint. This equation has also a gauge symmetry, and also its gauge parameter has a constraint. We call this trace constraint, and this is double trace constraint. But let us focus on this equation and this constraint. As you see, their equation of motion is in the position space and omega space. They showed that by gauge fixing, this equation can lead to the bosonic Wigner equations. Indeed, if you go to the Didander gauge, then you this is Didander gauge. If you this plus this and this is Didander gauge. In Didander gauge, you will get minus box on phi equals 0. In momentum space, this is p square on phi equals 0. This was one of equation of the Wigner. And then there is a residual gauge symmetry, and you can obtain other three equations. Okay. And however, this equation and its fermionic version that they obtained in this paper cannot be obtained from an action principle. This is why I called these equations non-Lagrangian CSP equation of motion. This cannot be obtained from an action. Indeed, if you consider this operator, then you will find that this operator is not Hermitian, and it cannot be obtained from an action. However, if you set mu equals 0 here and here, this equation is known as Franz-Stahl equation, and that equation can be obtained from an action. So the problem that this equation cannot be obtained from an action is this mu. However, there are two ways to obtain an action. One is going to the Fourier space of omega. I mean, if you write this equation by a trick in eta space, we will discuss about it later. If you write this equation in eta space, you will find that this equation can be obtained from an action, which is Schuster-Toro action. Another choice is to apply a field redefinition. By applying a field redefinition, you can get d omega dot d omega on phi equals 0. Indeed, you should use a field redefinition to omit this -1. Then that equation will be very complicated, but it can be obtained from an action, which is known as Metsayev action for continuous spin particle. The first bosonic CSP action, as I said, obtained by Schuster and Toro in 2014, and we obtained its fermionic analog in 1 year later. These are known as unconstrained formulation for continuous spin theory. I will explain how to obtain Schuster-Toro action from this non-Lagrangian CSP equation of motion. Okay, let us consider that equation, that bosonic non-Lagrangian CSP equation of motion, which was in this form with this constraint, and it has also a gauge symmetry and a constraint on gauge transformation parameter. But let us focus on these two. Performing a Fourier transformation, you can find that this constraint becomes in this form. It's so easy to see that d omega dot d omega -1 becomes eta squared plus 1. So I wrote this constraint in eta space in this form. And this equation now can be solved by this property of Dirac delta function. For Dirac delta function, we have this property. Also, we have another property, for example, x by delta x is 0, x squared by delta prime, which delta prime is derivative of Dirac delta function with respect to this argument. This is also 0. Using this property, you can find phi tilde should be in this form. This can be satisfied in this equation. Rewriting the bosonic non-Lagrangian CSP equation of motion in eta space, and then substituting this phi tilde here, you should take some derivative with respect to eta, because here you have eta. If you do that, you will get this equation, which is an Euler-Lagrange equation and can be obtained from an action. Indeed, this equation, this operator is Hermitian now, and it can be obtained from this action, which is known as Schuster-Toro action. So in 2014, Schuster and Toro obtained this action, which describes a bosonic continuous spin particle. It's a gauge field, so it should have a gauge symmetry, which is this. There is no constraint now here. There is no constraint on the gauge field and the gauge parameter. This is gauge parameter. This is gauge field. There is no constraint. And yes, But Schuster and Toro just presented this action. Here, I followed a procedure to obtain this action, because after that, we tried to obtain its Fermi-unique version. Using this manner, indeed, it's technical a bit, but it's so simple to follow. If you consider a Fermi-unique non-Lagrangian CSP, which was obtained by Jihad Murad and Xavier Beccard in 2005, we can write this constraint in eta space. Then you can solve this equation using Dirac delta function property. This psi theta should be in this form. If you put this here, and you should rewrite this in eta space, you will get this equation, which is an Euler-Lagrange equation and can be obtained from this action. It has also a gauge transformation, which this is a gauge transformation parameter. These two actions, at the end, we will want to supersymmetrize these two actions, which are known as Schuster-Toro formulation for continuous spin particle. Okay, CSP interactions with matter. We know that there are some no-go theorems like Weinberg's no-go theorem and so on, which state that in flat space there are no interacting theories of massless particles with a spin greater than 2. So higher spins particle, massless higher spins particle cannot be interacting in flat space. The assumption to obtain this no-go theorem is this: helicity states are boost invariant. If you boost, for example, a spin 2, it goes to itself. You will get again a spin 2. So each state are boost invariant. This is the base that Wigner says that massless higher spin particles cannot be interacting in flat space. However, in CSP case, helicity states are not boost invariant, and they mix under boost. So CSP may be interacting in flat space. This is what Schuster and Toro mentioned in this paper in 2013. They said that, as you see here, for example, for the bosonic CSP, if you boost this state, for example, this to spin 2, it goes to all states. It mixes with all states. As they showed in this paper, you will have a Bessel function which mix all states. So each CSP states are not boost invariant. So this CSP particle can be propagated in the flat space. However, for higher spins, they can be interacting just in ADS space. Using this fact that CSP can be interacting in flat space, in light conformalism, Metsayev studied consistent cubic vertices involving one CSP field and 2 arbitrary spin massive fields, and also 2 CSP fields and 1 arbitrary spin massive fields. You see, he said that such a cubic vertex can be possible if you have a CSP and 2 massive particles with any spin, and also if you have 2 CSPs and 1 massive particle here. He showed that cubic vertices including 3 CSPs is not possible. And also here, this particle should be massive. If this particle becomes massless, such a vertex cannot be possible. For this case also, if these two masses become 0, such a vertex cannot be possible, but one of them can be 0. One of these massive particles can be 0. In addition, Metsayev showed this in light cone formalism. In covariant formalism, we found that two scalars with distinct masses can interact minimally with a CSP. Indeed, we introduced a Berns-Berger-Van Dam-like current, which is this, with such a derivatives here, using these two massive particles with masses of m1 and m2. They should have unequal mass to lead to a mu. Mu is continuous parameter. Our case is like this case of Metsayev. Our result also published simultaneously in this year.
Sorry, can I just clarify real quick? So
yes.
Is the statement here that the continuous spin particle can only, or that two scalars with these very particular masses can interact with the CSP? So when you say mu is lambda m1 squared minus m2 squared, is it saying that there's no consistent interaction if that relation is not obeyed?
You mean if their masses are equal?
Or if the right hand side is just not equal to mu for our continuous spin particle, is there a consistent interaction?
If I understand your question, you mean if I choose equal mass to get a 0 mu?
Sure. Okay.
Yes. In that case, you will get a higher spin result. Indeed, before this paper, Xavier Beccal and Jihad Murad discussed such a case for higher spins with equal mass. This is why our case for equal masses, which leads to a 0 mu, will lead to the results of them for a higher spin case.
So if I have a continuous spin particle with some fixed mu, then that's saying that the scalars it interacts with have to obey this relation.
Yes, yes.
Okay.
Yes, exactly.
Yeah. Great.
Yeah, but you see, we worked in covariant formalism. In covariant formalism, we couldn't show that these masses can be equal and still we can have a continuous spin, you know. But here in the light cone formalism, Metsayev showed that these M1 and M2 can be equals. In light cone formalism, it's easier to work, but in the covariant formalism, it's so complicated, and we could just show this case with unequal mass, but with equal masses. Metsayev showed that showed that it is possible.
Great, thanks.
You're welcome. Okay, let us go to the supersymmetric continuous spin gauge theory. As I said, in the Schuster-Toro formulation for CSPs, there are no constraints on the gauge fields and the gauge parameters. And we worked in eta space. There are another formulation for CSP, which obtained by Metsayev in 2016 for bosons and 2017 for fermions, which there are some constraints on the gauge fields and gauge parameters. And he worked in omega space. This formulation is known as a constant formulation, and Schuster-Toro formulation is known as a unconstant formulation. But they are related to each other. We supersymmetrized both formulations in component formalism. But there are other approaches for SUSY CSP by Buchbinder, Gates, Kotrolikos, and other people. We know that in all SUSY theories, the number of bosonic degrees of freedom should be equal to the number of fermionic degrees of freedom. However, for CSP, we know that a bosonic or fermionic CSP has infinite number of degrees of freedom. So for a CSP supermultiplet, there would be 4 possibilities. We cannot say that the number of bosonic degrees of freedom should be equal to the fermionic case. We will have such possibilities. We can say that CSP is real or complex, and for the fermionic field, it can be Majorana or Dirac. Note that we didn't discuss about while CSP. We showed that yes, as you know, in the massless Dirac field, massless Dirac equation, for the massless Dirac equation, you can decompose it into 2 while equations. But for CSP, for fermionic CSP, due to the existence of mu, this mu plays a role like mass in the massive Dirac equation. So we showed that fermionic continuous spin equation cannot decompose into 2 while equations. This is why here I just speak about Majorana and Dirac CSPs. We showed that among these 4 possibilities, just in this case is possible, and just for this case, you can close SUSY algebra such that CSP is complex and CSP no is a Dirac spinor. The fact that we should have a complex CSP in the supermultiplet is related to the presence of the spin 0, as you see in this spectrum. For the bosonic CSP, we had spin 0, which should be complex in the chiral supermultiplet. This is why we should have a complex CSP here. Okay. In the Schuster-Toro formulation, you can consider this SUSY CSP action, which is a sum of this is Schuster-Toro action and this is our action, which B and F operators are in this form. I showed these equations separately before. For this SUSY CSP action, we found that this is invariant under these SUSY transformations, which epsilon is a SUSY parameter. And we showed that the algebra can be closed on shell. This means that we use the equation of motion, the fermionic equation of motion, up to a gauge transformation. For the Metsaev case, for Metsaev formulation, as I said, this formulation is so complicated. He wrote his actions in ADS space, but as you see, in flat space, they are still so complicated. There are many terms here, 5 terms here, 6 terms proportional to mu, 4 terms proportional to mu square, and for the fermionic action, there are 7 terms here proportional to mu. Again, for this case, we showed that this action, this SUSY action, is invariant under these SUSY transformations. We have also 5 terms here proportional to mu. And I wrote just these 2 terms to show that these are related to the chiral multiplet. These are related to chiral multiplet, yes. Again, we showed that the algebra can be closed on shell up to a gauge transformation. To be honest, I couldn't at first obtain these transformations for this action. I first obtained these transformations for Schuster-Toro formulation. Then I applied Fourier transformation. I went to omega space and could find this transformation and check that these are really this action is really invariant under these transformations, and the algebra can be closed. As we said, at mu equals 0, continuous spin representation becomes reducible and decomposes into the direct sum of all helicity representations. A CSP theory at mu equals 0 becomes an infinite sum over all higher spin theories. So for CSP supermultiplet, we expect to this supermultiplet decomposes into chiral multiplet plus half integer spin supermultiplets and integer supermultiplet. Yes. Indeed, as you can see, a CSP supermultiplet at mu equals 0, when mu goes to 0, this decomposes, and you can get chiral multiplet plus half integer spin supermultiplets and integer spin supermultiplets. Okay, in conclusion, CSP is a massless, as I said, CSP is a massless elementary particle introduced by Wigner. It's a unitary irreducible representation of the Poincaré group. It characterizes by continuous spin parameter called mu. Representation decomposes into a direct sum of all helicity representations at mu equals 0. It has infinite degrees of freedom per space-time point. Wave equations were introduced by Wigner. It has two types of representations, bosonic and fermionic. It can be interacting in flat space. And we studied its supersymmetrization and found that supermultiplet decomposes into a sum of all higher spin supermultiplet. Open problems for this field is investigation of CSP in condensed matter systems. There is one paper by Schuster-Toro. They work in 2+1 dimensions, and they said they claimed that a CSP in 2+1 dimension is a generation of massless onions. I'm not familiar, just I said this because maybe some people are interested in CSP in condensed matter systems. Group theoretical meaning of CSP in ADS is not obvious, although Metsayev wrote his actions in ADS space, but its group theoretical meaning is not clear. ADS CFT correspondence for CSP is interesting. Chern-Simons version of CSP can be possible. Off-shell SUSY CSP, as I said, our work and works of other people are on-shell SUSY CSP. So off-shell SUSY CSP is also interesting. And thank you for your attention.
Awesome. Thank you, Mojtaba. So if there are any lingering questions, maybe in the last part of the talk, I think this is a good time to ask them now.
I have a question.
Yeah.
In the SUSY action that you wrote, you had box plus 5 or 6 terms plus terms proportional to mu.
Yes.
So the mu independent terms, are those the Frontstahl operator?
Yes, yes,
Okay.
yes, exactly. When you tend mu to 0, you
Yeah.
will get exactly Franstad.
Right. Okay.
Yes.
So in the kind of ADS story, so is the action, well, is there a sense in which sending, so the statement was that there is an action for these continuous spin particles in ADS?
Yes, yes.
Can we send mu to 0 and like recover Vasiliev action in ADS? I mean, well, there is no Vasiliev action. But
No, no, you know,
like what goes wrong with that?
No, you know, indeed, Vasiliev equation is a nonlinear equation.
Yes.
But here in the CSP case, this is linear.
Gotcha.
In both cases, in ADS and in flat space. And maybe if someone construct a nonlinear CSP action, it can be related to Vasiliev equation, but at the level of equation of motion.
Right. So I mean, as in flat space, we couldn't write down, say, a 3-point vertex with 3 continuous spin particles. But do you know if something is possible like that for an ADS?
There is no paper on this. There are just 2 papers, as I showed, Metzev paper and our paper, which we are discussing CSP interactions with matter just in flat space.
Mm-hmm.
You know, higher spins, massless higher spins are not interacting in flat space, but they are interacting in ADS space. So in ADS space, you have a lambda, which has a dimension of mass. Here, in the CSP case, you have a mu, which has a dimension of a mass. It plays a role like lambda.
Oops. Mojtaba, we lost you. Are you still there? Mojtaba, can you hear us? You're muted.
You're muted though. So.
You're muted.
Yeah. Sorry, I don't know what happened. So in ADS, you have lambda, which has a dimension of a mass. So your theory is interacting in ADS space. But in the continuous spin case, since you have mu, which has a dimension of a mass, your theory is interacting in flat space. Mu plays a role as lambda in ADS. So it doesn't need to go to ADS and find CSP interactions in ADS. For CSP case, it is enough to work in flat space. But it would be interesting to find interacting CSP theories in ADS space. In that case, you will have 2 parameters, 2 dimensionful parameter. I mean, mu and lambda.
I thought
sorry, go ahead.
I thought Metsev's classification for cubic interactions in light-cone formulation included ADS interactions of CSP.
You mean Metzev?
Maybe I'm wrong. Maybe,
no. Just Metzev just discussed CSP in flat space, but he discussed continuous spin tachyon.
Okay.
He called it massive continuous spin particle. Massive continuous spin particle is a continuous spin tachyon.
So this is a naive question I really should have asked at the very beginning.
Yes.
But when we say continuous spin, just so the representation space looks like the spectrum of, say, JZ eigenvalues, right? Is like it's integers shifted by mu, right? If I'm remembering, is that roughly the idea? That so instead of a spin 0, 1, 2, you have spins, you know, mu plus 1, mu plus 2. You have is that the idea here, or? So just what is the representation space for a continuous spin particle look like?
Indeed, if you use induced representation for Poincaré algebra, for massive representations, you can go to the little group, and the little group for massive particles is SO3. For massless, for helicity representations, the little group is SO2. You should go to the two-dimensional plane, and your generator is J3, JZ, and your little group is SO2. But for continuous spin, your little group, your short little group is SO1. You know, for SO3, you have a sphere. For SO2, you have a circle. For SO1, you have a point. O1 has 2 points, but SO1 has 1 point. This is why in 4 dimensions, we have just one kind of bosonic CSP, or bosonic or fermionic CSP. In this case, the bosonic CSP is like a scalar. Some people called it a scalar continuous spin field. But if you go to higher dimensions, you may have, for example, a vector CSP, something like this.